Hi everybody, Jonathan here. This video is going to be my take on section 2.5, which is all about continuity. We ultimately are going to be caring about when a function is continuous in its domain, but we have to build up to that idea. So the first step is to define what it means for a function to be continuous at a number. So a function is continuous at a number if the limit as x goes to a of f of x is equal to f of a. In other words, this is one of those boring limits. So if the limit of a function is boring at a, then the function is continuous at a. Once we have the notion of a function being continuous at a point, we can then define what it means for that function to be continuous on an interval. Namely, it's continuous on an interval if it's continuous at every number in the interval. And if the interval happens to contain one or both of its endpoints, then the function has to be continuous from one side or the other, since it's not even defined on the other side of that endpoint. And the book kindly gives this example where this function f of x equals 1 minus the square root of 1 minus x squared is continuous on the interval, on the closed interval minus 1 to 1, because it's actually going to be continuous from the right at minus 1 and from the left at 1. And the book goes on to tell us eventually that basically every single type of function you've ever learned about is going to be continuous everywhere in its domain. So polynomials, rationals, trig functions, exponential functions, logarithmic functions, they're all continuous everywhere in their domain. And the last key result about continuity is that the composition of continuous functions is again going to be continuous, as is stated in Theorem 9. So if you combine this theorem with the limit laws and what we just said about all the nice functions you've ever worked with being continuous everywhere in their domains, this means that every function that you can build using addition, subtraction, multiplication, powers, roots, function composition, build it however you like, and whatever you get is guaranteed to be continuous everywhere in its domain. So what's the big deal about continuity? Well, there's a lot of big deals about it. So generally, when we're first learning math at the calculus level, we only deal with nice functions. But in physics and engineering and lots of other disciplines, there's lots of not nice functions you have to deal with. So those functions may or may not be continuous. And it turns out that continuous functions are the nicest, the most well-behaved functions. And while you don't necessarily know why that's to your advantage, think of it this way. Suppose you have to work on a project and you're choosing who you're going to work with. Do you want to choose a bunch of people who are going to get along with everyone, or do you want to choose a bunch of people who are kind of jerks to everyone? And it's not too hard to see. You'll be able to do a lot more. The project is going to be a lot more successful if you choose the nicer people. So continuous functions are nicer in the sense that down the road, we're going to be able to do a lot more with continuous functions than we are with not continuous functions. So knowing a function is continuous is going to go a long way to letting us do lots of great math with it. So earlier I told you that not all functions are well behaved, and in fact the canonical example of that is the function y equals sine of 1 over x. Now its domain is every real number except for x equals 0, and believe it or not, it is going to be continuous everywhere in its domain except at 0, but at 0 we got this crazy thing where it's oscillating infinitely many times in any interval around 0. So it's a very poorly behaved function, and that's going to make it harder to do exciting math with it. However, we can modify the function a little bit. If I go ahead and stick an x in front, then we get this function. And this function, while it still doesn't have x equals 0 in the domain, I could define it piecewise and make it actually equal 0 when x is 0. And this function is kind of fun because it sort of reminds me of a fractal. When you zoom in and in and in, it always kind of looks the same. But it turns out this function is going to be continuous, even at 0. Now, I know I just said that you would have to wait a while in order to see what continuous functions get for you, but in fact, one of the most important theorems is in this very section, which is the intermediate value theorem, and it only holds for continuous functions. And it's one of these statements that's kind of obvious, I suppose, but it's actually a little bit tricky to prove, so we're not going to prove it at this level. But it says that if f is continuous on a closed interval a and b, then any number between f of a and f of b is going to get hit by f for some value c in between a and b. And while that seems, I don't know, perhaps it's hard to understand the significance of this, but you can go ahead and use the intermediate value theorem to do things like finding roots of polynomials and things like that. So it's already we can already use it to come up with algorithms to find roots for polynomials that we'd have no other way of finding the roots of, and lots of other applications. In fact, we'll be seeing a lot of the intermediate value theorem later on in the course.